we are doing more AP review. This is 2019 BC Free Response 6. A function f has derivatives of all orders for all real numbers x. A portion of the graph of f is shown above. My graph is really crappy. There's a better graph on the actual AP question, which I'm looking at while doing this, but this is just so I can point to things. Anyway, along with the line tangent to the graph at x equals 0, selected derivatives of f right here are given in this table. Again, derivatives at 0. Cool. So part A, write a third degree Taylor polynomial for f about x is 0. Okay, so for part A, right, just a reminder of how a Taylor series works, right? It's f of a plus f prime of a over 1 factorial, which we don't have to write, times an x minus a to the first. Again, we don't have to write to the first, plus f double prime of a over 2 factorial times x minus a to the second, right? And then f triple prime of a over 3 factorial, x minus a to the third, right? And so on, right? So here we're using a as 0, which is why we have all these values of derivatives at 0, right? So a couple important things that we can get from this graph, right? This graph not only gives us that f of 0 is a 3, which we're going to need for this thing when we do f of 0, but it also gives us the derivative because we can see that the tangent line has a slope of down 2, right 1, so f prime of 0 has to be a negative 2. Right? So again, what we're able to get from this is this value and also this value. Cool. So when we go to do part A, and the rest of them are given on this table, right? So part A, they said the third degree Taylor polynomial. That means go up until x cubed, which will be this term. So I'm going to call it p sub 3 of x, right? And the first term should just be the constant that is f of 0, which in this case will be, now if you need to write f of 0, you can, or you can just jump to writing that f of 0 is 3. That's fine. Plus f prime of 0, well, we now know that's a negative 2, so I'm just going to write a minus, times x minus a, which is x minus 0, so I just need the x, right? Plus, and now I know the second derivative of f from the table. So the second derivative of f at 0 is 3, so plus 3 over a 2 factorial, which is just 3 over 2, right? And then x squared, because it would be x minus 0 quantity squared, right? And then I know the third derivative, right, which would be this guy. This is a negative 23 halves divided by a 6. So that should be a negative 23 twelfths. And then it would be x minus 0 to the third, which we're just going to write as x cubed. So that's my third degree Taylor polynomial, right? Remember, it doesn't mean 3 terms. It means goes to the third degree. Cool. All right, let's talk about part B. So for part B, we're asked to write the first 3 non-zero terms for the Maclaurin series for e to the x. So for part B, there are 2 skills, right? The first skill is to write the first 3 non-zero terms for e to the x, right? So e to the x is approximately 1 plus an x squared over 2 factorial, which is just a 2, right? So it's not, I was able to write approximate. If I wanted to write equal, I would have to put a dot, 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 because it's actually equal to the infinite series. So that's what I want. Second part of this question is write the second degree Taylor polynomial for e to the x times f of x. Now I'm not going to use p because I used p for just f, so I'm going to use something like q sub 2, right? So so now I want to take e to the x times f of x, and I want to write some Taylor polynomial. Now because I want the second degree Taylor polynomial, right, what I'm basically doing is I'm taking this thing and I'm foiling it with this. The problem is that both of these actually go on forever, right? This is dot, dot, dot technically, and this is dot, dot, dot technically, if we were doing the entire Taylor series, not just the Taylor polynomial. But in reality, I don't want it to go forever. I want the second degree Taylor polynomial. So I say to myself, well, cool, if I look at the terms of this series, right, if I look at the terms of this e to the x and the terms of this thing, right, I recognize that that means I want to go up as high as a second degree. So when I take e to the x, I'm going to take a 1, right, plus this x squared over 2, right? But when I do this, let's say q sub 2 of x, right, this 1 is going to get multiplied by all of these terms if I were doing the infinite series, but I'm not doing the infinite series. I'm only going up to the second degree. So I say, well, how far would I have to multiply this 1 by in order to get up to a second degree? Well, because a 1 is a constant, I would have to multiply it by these first 3 terms. I don't need to multiply it by this term because that would be an x cubed, and I only want the second degree Taylor polynomial, right? I'm going to add to that what happens when I multiply the next term in e to the x, which is an x. Well, now I say, cool, I'm already starting with an x. So what I'm going to have to do is multiply by the 3, but also the 2 minus x. I don't bother with the 3 halves x squared because I know that that would give me a cubic, and I only want the second degree Taylor polynomial, right? And then I take the last term of e to the x, which is x squared over 2, and I realize that the only thing I can multiply this by is the 3, because if I multiplied it by the negative 2x, I'd get an x cubed again. So the highest degree I get for any of these is an x squared, which is what I want for a second degree Taylor polynomial, hence q sub 2. Now, this is great, and this is the work behind it, but then I need to clean this up, because they're going to want this written as a nice, happy polynomial. So when I distribute, I'm going to get a 3, a negative 2x, and a plus 3 halves x squared. When I distribute this guy, I get a plus 3x and a minus 2 x squared, my bad, mea culpa, right? And this guy is just a plus 3 halves x squared. Now, I conveniently wrote this in a way that I could just be lazy and combine my like terms. So what I notice is that I end up getting a 3 as my constant term, a plus x as my linear term, and when I clean these guys up, I get a 6 halves, right? I get a 6 halves, so that would be 3 minus a 2, so that ends up being plus an x squared. Sorry, my brain kind of froze for a sec. So this is my answer for q sub 2 of x, right? So that's my second degree Taylor polynomial for this thing. All right, cool. Again, I'd use q instead of p because if p was the polynomial that I'm using for f, then when I do a different function, and e to the x times f would be a different function, I need a different letter. Cool. Okay, part C. Let h be the function defined by h of x equals the integral from 0 to x of f of x dt. Use the Taylor polynomial found in part A to find an approximation for h of 1. Cool. So I'm going to keep my part A since I have to use part A. And I'm lazy and don't want to have to start from scratch. So for my part C, I know that h of x is the integral from 0 to x of f of t dt, right? They want me to approximate h of 1. Well, h of 1 should be the integral from 0 to 1 of f of t dt, right? But if I approximate it using the f I found here, right, that would be the integral from 0 to 1 of 3 minus 2x plus 3 halves x squared minus 23 twelfths x cubed with respect to x, right? So when I integrate this, I'm going to get that h of 1 is approximately a 3x minus an x squared plus a 1 half x cubed minus a 48, sometimes my brain is a little bit slow, 48 x to the 4th, evaluated from 0 to 1. So when I do this and plug this in, I'm going to get that this is a 3 minus a 1 plus a 1 half minus a 23/48 minus what thankfully comes out to be a boatload of 0 because this is already super fun. So the common denominator I want is everybody over 48, right? So I'm going to get, well, that's not fun at all, 150 less 6, right? So $1.44 minus a 48 plus a 24 minus a 23 all over 48. So when I combine my stuff and things, this is a plus 1. This should be 4 shy of 100, so it should be a 96. So I should get a 97 over a 48. Yay! So my h of 1 is approximately a 97 over 48, and boy, was that fun. All right, cool. Part D. It is known that the Maclaurin series for h converges to h of x for all real numbers x. It is also known that the individual terms of the series for h of 1 alternate in sign and decrease to an absolute value of 0. Use the alternating series error bound to show that the approximation found in part C differs from h of 1 by at most 0.45. Cool. So essentially what we need to do is take the next term in the sequence, max it out, and the error has to be less than that. So notice that this went up to the third term, right? So in order to find the error, we need to use the term after the third term. So that's why they gave us that last line in the table. Now, sometimes they give you the last line in the table just 2019 BC free response 6, because I did something stupid when I was doing part D, so I'm fixing it now. All right, so part D wants the error when we approximate h, right? So the trick is that if you look at h, right, h of x is the integral from 0 to x of f of t dt, right? So essentially, the h function, right, is going to use the integral of the f function, right? So when you want the error for h of 1, right, the error should be less than or equal to whatever the next non-zero term is, right? Well, the term we didn't use was this one for f, right? The term we didn't use for f would have been a fourth derivative of f at 0. Oh, my bad. Sorry. A fourth derivative of f at 0, x to the fourth over a 4 factorial. That's the term we wouldn't use. But that's not the term for h, because h is the integral of f. So the term we wouldn't use for this would have been an f of 4 evaluated at 0, x to the fifth over 5 times 4 factorial, because I'd have to integrate this term. So when I max out this term, right, so I want to max this out on the window from the center to the value I was asked to plug in. Now it happens the center is the smaller value here, but basically we just mean the window between whatever the value is and the center in whichever order they happen to occur. So if the value I'd been asked to plug in was a -1, it would be -1 to the center, so -1 to 0 versus 0 to 1. When I max this out, this is a quantity I know. This is a 54, right? 54 times, when I max out x to the fifth on this window, it's a 1 to the fifth, over a 5 times 4 times 3 times 2 times 1, which I can clean up by canceling a bunch of stuff. So I recognize that 54 is a 9 times a 6, and that 6 is going to cancel. So I end up getting that the error is less than or equal to the absolute value of 9/20. Well, I was asked to show that the error is smaller than that is at most 0.45. Well, that's exactly what that quantity is, right? So that's 9/10 divided by 2, so 0.45. So I showed that the error was, in fact, at most 0.45.